Let's talk about the simple machine of a wedge now. It's similar to an inclined plane. We'll start with an inclined plane real quick just to revisit that. An inclined plane is where you have an object with some resistance, some load, that we'd like to get to an elevated surface, and it's hard to just pick up and get it to this level over here, right? And so instead of having to pick it up and get it on the platform, we use an inclined plane, and we imagine we push it or roll it up. So we travel this distance here, which is a longer distance than just going straight up. So we cover more ground to get that mechanical advantage. The distance of resistance, the distance we were trying to overcome, was this distance right here. Okay, with a wedge, it's similar but a little different. Instead of rolling the object up this inclined plane, the inclined plane is now going to become the wedge. Now I don't have gravity here working for me on the, laying these on the side, but the idea is that the wedge now is a moving inclined plane. Okay, so it's being pushed. There's a force of effort pushing, and as I'm kind of pushing this wedge to wedge between two items, then the object is forced to, in essence, go up the inclined plane, or for the wedge to start to separate these two items, like that. So hopefully that's a little visual aid for you to understand. So let's think about the ideal mechanical advantage. Ideal mechanical advantage of a simple machine is the distance the effort travels divided by the distance of the resistance. Okay? Well, the effort, we'll start there. Think about this wedge and the effort. We're going to apply an effort back here, right? We're going to drive this wedge. And so we're starting right here. But in the end, this is where we'd like to end up. We would like to drive this wedge between two objects to get it to separate these. So if we start from back here and we end over here, this distance right here would represent the distance traveled of the effort. And as this wedge is driven in between these two objects, we see that we get separation. Okay, we go from which is supposed to be really no separation, kind of just illustrated, left a little space. You can see there's two objects, but imagine this is basically 0. We're just kind of wedging into a crack, and as we drive that, we get this much, which is the width of the wedge. So that distance right there, the width of the wedge, is the distance of the resistance. So that is where you're going to get the dE and the dR to calculate ideal mechanical advantage. Now, if they ask you for the actual mechanical advantage, or refer to that, actual mechanical advantage, like all of the other simple machines, is found using the forces. So the resistance force divided by the effort force. So in that case, we would want to know how much was the effort applied, and then how much resistance is there between these. And that'll potentially may be given to you. If you think of algebraically these formulas in a word problem that might be presented, you basically have 3 variables, right? 1, 2, 3. And same over here. 1, 2, 3. Algebraically, as long as I give you 2 out of 3, you should be able to find the missing 1. So you won't always be asked to calculate a mechanical advantage. Sometimes the problem will give it to you, and if they give it to you, they most likely are giving you one of these two, or maybe with distances, but give you one, the resistance or the effort, and asking you to find the other. So let's just say, for example, if they said, hey, this has a mechanical advantage of 10, and the resistance force is 500 pounds, find the effort force. Then you can see, after plugging in your numbers, there's only one unknown left. So just FE. And it just requires a little bit of math, a little bit of algebra just to manipulate this. So with the FE in the denominator, I would divide both sides by FE. That clears the variable out of the denominator, cancels it out here, but then it reappears on the other side. That's multiplication. I multiplied both sides. And then I turn my attention to the left side of the equal sign because that's where the variable is. And then I would say, okay, how do I get 1 FE, not 10 times FE? So then I would divide both sides by 10. I'll just rewrite that real quick. So FE times 10, and I would divide by 10. And whatever I do to one side of the equation, I need to come over here and do to the other. So remember, those canceled. I had only the 500. So we would divide both sides, again, by 10. The 10s cancel here, leaving your answer of the effort force. And this was nice. We get 50.